Take the chair you are sitting on right now, or the floor beneath you, or the wall nearest to you, whatever solid object is closest to your body at this moment. Something that feels continuous and dense and real in the way that only physical objects feel real. The way matter feels when you press your hand against it and it pushes back, and you know without any doubt that something is there. Now consider what that object actually is at the scale where physics operates. Every atom in that object consists of a nucleus surrounded by electrons. The nucleus contains the overwhelming majority of the atom's mass, protons and neutrons packed together in a dense core. The electrons occupy a region of space around that nucleus called the electron cloud. Between the nucleus and the electron cloud, there is nothing. No matter, no particles, no substance of any kind, just space. And the ratio of the size of the nucleus to the size of the atom, the ratio of the dense core where almost all the mass lives to the total volume the atom occupies, is approximately 1 to 100,000. If you scaled a hydrogen atom up until its nucleus was the size of a marble, a small glass marble sitting in the palm of your hand, the electron would be orbiting at a distance of approximately 1 mile. 1 mile from a marble, with nothing in between. The space that feels solid when you press your hand against it, the space that supports your weight and holds the shape of every object you have ever touched, is almost entirely empty. The matter in it occupies approximately 100,000th of 1% of its volume. Everything else is void. This is not a metaphor. It is not a simplification for educational purposes that breaks down under closer examination. It is the actual structure of matter as physics understands it. The world you experience as solid and continuous and present is, at the scale where atoms operate, almost entirely empty space, with a few extraordinarily tiny concentrations of mass and energy distributed through it at vast intervals relative to their own size. And that is just the beginning. Because when you move from the scale of atoms to the scale of the solar system, and then from the scale of the solar system to the scale of the galaxy, and then from the scale of the galaxy to the scale of the observable universe, the emptiness does not get less extreme, it gets more extreme. At every scale of magnification, at every level of zoom, the overwhelming character of the universe turns out to be the same. Emptiness, void, space between things that dwarfs the things themselves by factors that have no meaningful analogue in ordinary human experience. Tonight, we are going to follow this emptiness from the inside of an atom to the edge of the observable universe. We are going to let it be as large as it actually is. We are going to sit with what physics actually says about the structure of matter and space and the cosmos. Not the comfortable summary, not the version that preserves the intuition that the world is solid and full and present in the way it feels. The version that is actually true. Before we begin, if you are here because the night is long and you need something to carry you through it, stay with this. What follows will take your sense of where you are and what surrounds you, and make it larger and stranger than it was before you started. Let us begin at the smallest scale we can meaningfully discuss. Let us begin with the atom. The atom is the basic unit of ordinary matter. Everything you can see, touch, smell, taste, or interact with in any way is made of atoms. The chair, the floor, the air you are breathing, the food that became your body, the body itself, all of it is atoms. There are approximately 118 known types of atoms, the elements of the periodic table, distinguished from each other by the number of protons in their nuclei. Hydrogen has 1 proton, carbon has 6, iron has 26, gold has 79, uranium has 92. Every different element, every different chemical property, every different material in the universe derives from differences in this single number: how many protons are in the nucleus. The nucleus itself is extraordinarily small. A hydrogen nucleus, a single proton, has a diameter of approximately 1.7 femtometers. A femtometer is 10 to the power of negative 15 meters, a millionth of a billionth of a meter. Numbers at this scale are impossible to visualize directly, so let us use the scaling approach. If you magnified a proton until it was the size of a period at the end of a sentence, approximately 1 millimeter in diameter, you would have magnified it by a factor of roughly 600 trillion. At that magnification, a hydrogen atom would be approximately 600 meters in diameter, more than half a kilometer. A dome 600 meters wide, with a single millimeter scale dot at its center and nothing else inside. That nothing else is important. The space inside an atom is not occupied by any classical physical medium. It is not filled with a gas or a fluid or any substance we can describe using the concepts of ordinary experience. It is occupied by the quantum mechanical probability distribution of the electron, a mathematical description of where the electron is likely to be found if you measure it, which is everywhere in the electron cloud simultaneously, in a sense that classical physics cannot accommodate. But the electron itself, when it manifests as a particle, is approximately as small as or smaller than the proton. The 2 tiny particles at the extremes of this vast atomic volume, with nothing between them that can be described as matter in any ordinary sense. The emptiness of the atom is not a quirk of hydrogen. Every element has the same basic structure: a tiny, dense nucleus containing almost all the mass, surrounded by electron clouds at distances enormous relative to the nuclear size, with nothing substantial between them. The specific geometries vary. Multi-electron atoms have electron clouds in different shapes and at different distances, and the nuclear size grows with the number of protons and neutrons, but the ratio of occupied to unoccupied volume remains essentially the same. Matter is almost entirely empty space at the atomic scale. The solidity and continuity you experience when you press your hand against a surface is a consequence of electromagnetic forces, the repulsion between the electron clouds of adjacent atoms, not a consequence of matter being genuinely dense or continuous of the scale where atoms operate. Now let us go to the next scale up. Let us go from atoms to molecules to the macroscopic matter that makes up the objects of everyday experience: the chair, the floor, the wall. At this scale, the atoms are packed together. In solids, they are held in fixed positions by chemical bonds. In liquids, they flow past each other while remaining in contact. In gases, they move freely through large volumes with occasional collisions. In all cases, the atoms are close together relative to atomic dimensions. The interatomic distances in solids and liquids are a few times the size of the atoms themselves. The emptiness inside each atom is still there, but the atoms are so densely packed relative to their own size that the material feels genuinely continuous and solid. But even here, even at the scale where matter feels most real and most present, the emptiness dominates. Consider a cubic centimeter of iron, roughly the volume of a small pebble. It contains approximately 8.5 times 10 to the 22 atoms, a number so large it is essentially meaningless without context. Each of those atoms is mostly empty space. the actual nuclei and electrons, the actual matter in that cubic centimetre of iron, occupy approximately 10 to the negative 12 times the total volume. 1 trillionth. If you somehow compressed the iron in that pebble until only the nuclei were left, removing all the empty atomic space, the pebble would shrink to a volume smaller than a single atomic nucleus, a dot invisible to the naked eye, but containing the same mass as the pebble. This is not a thought experiment. It is what actually happens inside neutron stars, the remnants of massive stars that have undergone supernova explosions. In a neutron star, the gravitational pressure is so extreme that the electron clouds of atoms are crushed inward. The electrons combine with protons to form neutrons, and the material collapses to nuclear density. A neutron star with the mass of the Sun, our Sun, 333,000 times the mass of Earth, has a diameter of approximately 10 to 20 kilometers, about the size of a city. The Sun's worth of mass compressed into something the size of a city, because the empty space inside all those atoms has been removed. This is what matter actually is. Not the dense, continuous substance of everyday intuition. A sparse collection of extraordinarily tiny particles, separated by vast emptiness, held together by forces that make the emptiness feel like solidity when you press against it. The rock feels hard, not because it is full, but because the electromagnetic forces between its atoms resist compression with a strength that far exceeds anything your muscles can apply. If those forces were removed, if the electromagnetic repulsion between electron clouds somehow switched off, you would fall through the floor, through the earth, through everything, because there is essentially nothing there to stop you. Now let us go to the scale of the solar system, because if atoms are mostly empty space, the solar system is even more so, and by margins that make the emptiness of atoms look crowded. The solar system consists of the Sun, 8 planets, dozens of moons, hundreds of thousands of asteroids, billions of comets, and a diffuse cloud of gas and dust extending outward for tens of thousands of astronomical units in what is called the Oort cloud. The total mass of all of this, everything in the solar system except the Sun itself, is approximately 0.14% of the Sun's mass. The Sun contains 99.86% of all the mass in the solar system. Everything else, every planet, every moon, every asteroid, every comet, every mote of dust and molecule of gas in the entire solar system is a rounding error on the Sun's mass budget. And the Sun itself, enormous as it is, 1.4 million kilometers in diameter, 333,000 times the mass of Earth, so large that 1.3 million Earths could fit inside it, is a tiny dot in the volume of space the solar system occupies. The solar system extends to the heliopause at approximately 120 astronomical units from the Sun, about 11 billion miles. If you scaled the solar system down so that the Sun was a grapefruit, about 10 centimeters in diameter, the nearest planet, Mercury, would be a grain of sand 4 meters away. Earth would be another grain of sand 10 meters away. Jupiter, the largest planet, would be a marble 52 meters away. Neptune, the outermost planet, would be a pea 300 meters away, nearly 3 football fields from the grapefruit Sun, with essentially nothing in between. And the heliopause, the edge of the Sun's direct influence, where the solar wind meets the interstellar median, would be at approximately 1.2 kilometers from the grapefruit, more than a kilometer away. With 8 tiny planets and a handful of moons, and some small rocky and icy bodies scattered through that volume, and nothing else. No medium, no substance, just space, essentially empty, dotted with vanishingly small objects at vast intervals. This is the solar system. Not a crowded, busy system full of objects, an enormous volume of space that is, for all practical purposes, empty, with a modest concentration of matter at its centre and a sparse scattering of small objects distributed through the surrounding void. The images we are accustomed to seeing of the solar system, diagrams with the planets clustered together and the Sun visible in the same frame, are not wrong in their labels or their relationships, but they are profoundly wrong in their proportions. In an accurately scaled diagram of the solar system, where the Sun is visible as a disk, the planets would be dots too small to see with the naked eye, separated by distances that would require the diagram to be the size of a city block to represent accurately. Now let us go to the scale of the galaxy, because if the solar system is mostly empty space, the Milky Way is empty in a way that makes the solar system look crowded beyond imagining. The Milky Way is a spiral galaxy, approximately 100,000 light-years in diameter and roughly 1,000 light-years thick at the disk. It contains somewhere between 100 billion and 400 billion stars, depending on how you count the faint red dwarf stars that are difficult to detect individually, but that are thought to be extremely common. It also contains enormous amounts of gas and dust, the interstellar medium, distributed through the disk in a complex structure of hot, ionized regions, warm neutral gas, cold molecular clouds, and everything in between. The average distance between stars in the solar neighbourhood, the region of the Milky Way where our Sun is located, about 26,000 light-years from the galactic centre, is approximately 4 to 5 light-years. 4 to 5 light-years. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. 1 light-year is approximately 5.88 trillion miles. So the nearest star to us is approximately 25 trillion miles away. In the scaling analogy, where the Sun is a grapefruit 10 centimeters in diameter, Proxima Centauri would be another grapefruit located approximately 2,800 kilometers away, about the distance from New York to Denver. 2 grapefruits, 2,800 kilometers apart, with essentially nothing in between. The Milky Way contains between 100 billion and 400 billion such grapefruits, each separated from its nearest neighbour by distances equivalent to the separation between New York and Denver on our scale, scattered through a volume of space spanning 100,000 light-years. If you took all the matter in the Milky Way, all the stars, all the gas, all the dust, everything, and compressed it to the density of water, it would fit in a sphere approximately 260 light-years in diameter. The Milky Way occupies a volume roughly 100,000 light-years across. The matter in it, compressed to ordinary density, would occupy a sphere 260 light-years across. The rest, the other 99.9999% of the galactic volume, is empty. This is the galaxy, not a dense, rich environment full of stars and material, an almost incomprehensibly vast volume of space that is, at the scales relevant to navigation and travel, essentially empty, with a sparse population of stars distributed through it at intervals so large that the stars themselves are invisible to each other except as points of light in a dark sky. And the galaxy is not the largest scale of emptiness in the universe. It is not even close. Let us go to the largest scale, the scale of the observable universe. The the scale of the cosmic web, the large-scale structure that organizes the distribution of matter across the entirety of what we can see. The observable universe contains somewhere between 1 and 2 trillion galaxies. Each of those galaxies contains billions to hundreds of billions of stars. The total number of stars in the observable universe is estimated at approximately 10 to the power of 24, a septillion, a number so large that every comparison to human-scale quantities fails immediately. If every grain of sand on every beach on Earth represented a star, you would need approximately 10,000 Earths worth of beaches to match the estimated number of stars in the observable universe. And yet, the observable universe, 46 billion light-years in radius, a sphere of incomprehensible scale, is almost entirely empty. The matter in the universe, all the stars, all the galaxies, all the gas between galaxies, all the dark matter whose gravitational influence we can measure even though we cannot detect it directly, is distributed in a structure called the cosmic web. Long filaments of matter stretching across hundreds of millions of light-years, intersecting at dense nodes called galaxy clusters, surrounding vast empty regions called cosmic voids. The filaments are where galaxies congregate. The voids are where almost nothing lives. The Boötes void, a roughly spherical region of space approximately 330 million light-years in diameter, contains almost no galaxies. A sphere 330 million light-years across, in a universe rich with structure, and it is essentially empty. Not a region where galaxies are sparse, a region where they are nearly absent. The cosmic web has left this volume unfilled, and it has been unfilling it for billions of years as the expansion of the universe and the gravitational dynamics of the large-scale structure have drawn matter into the surrounding filaments and left the void increasingly vacant. The voids occupy the majority of the universe's volume. The filaments, where most of the matter lives, are thin relative to the enormous spaces they bound. The galaxy clusters at the intersections of the filaments are denser but still vastly empty compared to any human intuition of density. If you picked a random point in the observable universe and asked whether it was inside a galaxy, inside a filament, or inside a void, the overwhelming probability would be that it was inside a void. Empty space is not the exception in the universe, it is the dominant condition. Matter is the exception. Structure is the exception. Everything that exists in any form we can observe or interact with is a rare concentration in an overwhelming sea of nothing. At the scale of the observable universe, the emptiness is not 99.9%. It is not 99.99%. It is not 99.999%. The fraction of the universe's volume that contains matter at densities comparable to ordinary physical objects is so small that expressing it as a percentage requires so many nines after the decimal point that the number becomes meaningless. The universe is, for all practical purposes, empty. The matter in it is a vanishingly sparse collection of concentrations distributed through a volume of space so vast that the concentrations, enormous as they are on human scales, are negligible on cosmic scales. This is what the universe actually is, not what it looks like from Earth, where the night sky appears rich with stars and the Milky Way stretches across the sky as a band of light dense enough to cast shadows on a dark night. Not what it looks like in photographs taken by telescopes designed to gather light from faint and distant objects and compress it into images that make the cosmos seem crowded and complex and full. What it actually is, at the scales where physics operates, is overwhelming emptiness, punctuated by extraordinary rarities. The stars are the rarities. The galaxies are the rarities. The planets are more rare still. And life, the kind of complex chemistry organized into structures capable of experiencing and reflecting on the universe, is the rarest thing of all, as far as we know, in a cosmos almost entirely defined by its own emptiness. Now let us ask the question that this emptiness makes urgent. If the universe is 99.9999% empty at every scale, what is in the emptiness? Is it truly nothing? Or does the void contain something that our current understanding of physics has not yet fully grasped? The answer is that the void contains something, several somethings. Things that are not nothing by any definition of nothing that physics can currently offer, and whose nature and properties are among the most important and least understood questions in all of science. The first thing in the void is the quantum vacuum. Empty space in quantum field theory is not truly empty. It is filled with quantum fields, mathematical structures that pervade all of space and whose fluctuations give rise to all the particles and forces we observe. In their ground state, these fields contain energy, zero-point energy. The lowest possible energy state of a quantum field is not zero. It is a positive value, a residual energy that cannot be removed no matter how completely you evacuate a region of space of all particles and radiation. This zero-point energy is real. It has measurable physical consequences, most famously the Casimir effect, in which two uncharged metal plates placed very close together in a vacuum attract each other because the quantum vacuum between them is slightly different from the vacuum outside them. The quantum vacuum is seething with activity at the scales where quantum mechanics operates. Virtual particles, particle-antiparticle pairs that spontaneously appear from the vacuum energy and annihilate each other in times so short they cannot be directly observed, but that can be detected through their effects on nearby particles, are constantly flickering into and out of existence throughout all of space. The vacuum is not static, it is dynamic, it fluctuates, it has structure. It responds to the presence of matter and energy in ways that affect the behavior of particles and fields in its vicinity. The second thing in the void is dark matter. We have discussed dark matter in other contexts, the invisible mass whose gravitational effects are detected in the rotation curves of galaxies and the dynamics of galaxy clusters and the large-scale structure of the cosmic web. Dark matter fills the halos of galaxies and the filaments of the cosmic web. It is present everywhere that ordinary matter is, and in many places where ordinary matter is not. It pervades the voids, though at lower densities than in the filaments. It is, in a very real sense, the dominant material component of the universe's empty-seeming spaces. Not ordinary matter, not baryonic atoms, but whatever dark matter particles are, distributed through the cosmos at densities our instruments detect gravitationally, but cannot yet characterize directly. The third thing in the void is dark energy. The energy density of empty space itself, the cosmological constant, the thing that is driving the accelerating expansion of the universe, the 68% of the total energy content of the cosmos that exists uniformly throughout all of space, regardless of whether that space contains matter or not. Dark energy does not concentrate in galaxies or filaments. It does not cluster. It is the same everywhere, in the densest galaxy cluster and in the deepest cosmic void. It is the energy of space itself, and it is enormous in total. Even though its density per unit volume is extraordinarily small, because the total volume of the universe is so vast that even a tiny energy density per unit volume adds up to a dominating contribution to the total energy budget. Dark energy is the most extreme expression of the idea that the void is not empty. The apparently empty space between galaxies is not nothing. It is a medium with a real positive energy density that exerts a real, measurable effect on the evolution of the universe, driving the accelerating expansion that is carrying galaxies away from each other and that will eventually empty the observable sky of everything except our local group. The void is full of dark energy. The emptiness is energetic. The nothing is something. And we do not know what it is. We do not know what dark energy is any more than a medieval natural philosopher knew what gravity was. We can describe it. We can measure its effects with considerable precision. We can give it a name and assign it a value in our equations, but we cannot explain it. The most successful attempt to calculate its value from first principles, from quantum field theory's prediction of the zero-point energy of the vacuum, gives a result approximately 10 to the power of 120 times larger than the observed value. 1 followed by 120 zeros times too large. The largest discrepancy between theoretical prediction and experimental observation in the history of physics. The void is full of something. We do not know what it is, and the properties of that something are determining the fate of the universe. Let us talk about what the emptiness means for the question of whether we are alone. Because the emptiness of the universe is not just a fact about physics and cosmology, it is a fact about the probability of life and intelligence, and the likelihood that anything capable of asking questions about the universe exists anywhere other than here. The argument goes like this. The universe contains between 1 and 2 trillion galaxies. Each galaxy contains billions to hundreds of billions of stars. The total number of stars is approximately 10 to the power of 24. In recent decades, and particularly since the launch of the Kepler Space Telescope in 2009, we have learned that planets are extraordinarily common, that most stars have planetary systems, that rocky planets in the habitable zones of their stars are abundant, that the number of potentially habitable worlds in the observable universe runs into the billions of billions. The raw material for life, carbon, oxygen, nitrogen, hydrogen, the building blocks of organic chemistry, is distributed throughout the cosmos by stellar nucleosynthesis and the deaths of stars. The conditions that produced life on Earth do not appear to be uniquely rare at the level of chemistry and physics. And yet, we have found no evidence of life anywhere other than Earth. No signal, no artifact, no unambiguous detection of any biological or technological process occurring anywhere in the cosmos beyond our own planet. The universe is full of stars and planets and the raw materials of chemistry and the energy sources that chemistry requires. And as far as we can tell, it is silent. The technological civilization capable of looking for signals from other civilizations, ourselves, has been looking for approximately 70 years and has found nothing. This is the Fermi paradox. Named for the physicist Enrico Fermi, who allegedly asked at a lunch conversation in 1950 simply, "Where is everybody?" If the universe is as large and as old and as chemically rich as it appears to be, and if life tends to arise wherever conditions permit it, and if intelligence tends to emerge from sufficiently complex life, and if technological civilizations tend to expand and communicate and leave detectable traces of their existence, then the cosmos should be teeming with such civilizations, and at least some of them should be detectable from Earth. And yet, nothing has been detected. the sky is silent. The void is empty not just of matter, but apparently of minds. The emptiness of the universe makes the Fermi paradox more acute, not less. Because the emptiness means that the distances between potentially habitable worlds are vast. Even if life arises commonly around stars throughout the galaxy, the nearest living world might be hundreds or thousands of light years away. Any signal it sends would take hundreds or thousands of years to arrive. Any response to a signal we send would take the same time to return. The communication timescales imposed by the speed of light across the vast, empty spaces between stars make any civilization-to-civilization conversation essentially impossible in human terms. A single exchange would span more time than all of recorded human history. And the expansion of the universe adds another layer. The galaxies beyond our local group are receding from us at speeds that will eventually carry them beyond our observable horizon. Any civilization in those galaxies is already unreachable, not just by travel, but by communication. Any signal they send us now will arrive, if at all, after timescales that render the concept of a relationship between civilizations meaningless. The universe is not just empty of matter, it is structured in a way that physically isolates any civilization that arises within it from the overwhelming majority of all other civilizations that might exist elsewhere in it. If we are not alone, if life and intelligence arise commonly throughout the cosmos, then the universe is full of isolated civilizations, each separated from every other by distances that make communication and contact effectively impossible on any timescale relevant to the existence of a technological civilization, each looking outward at an apparently empty sky, each perhaps reaching the same conclusion we have reached, that the universe appears empty of other minds, without any of us being wrong. The emptiness would be a structural feature of a cosmos designed, whether by physical law or by the anthropic selection of observers, to produce minds that find themselves alone, regardless of how many other minds might exist. This is one of the most disturbing implications of the universe's emptiness. Not just that space is mostly void, but that the void is large enough and expanding fast enough to ensure that any intelligence arising within it finds itself effectively alone, separated from any potential neighbors by distances that make isolation the default condition of conscious existence in the cosmos. We are not alone in the cosmos as a matter of fact, but we may be alone in the cosmos as a matter of experience, unable to reach or detect or communicate with any other intelligence, even if the universe is full of them, and unable to distinguish this condition from actually being alone. The physicist Enrico Fermi, who asked where everybody is, also helped build the first nuclear reactor and contributed to the Manhattan Project, and did foundational work in quantum mechanics and particle physics. He was not a man prone to facile questions. When he asked where everybody was, he understood the implications of the question. He understood that the size and age of the universe, combined with the apparent absence of any detectable extraterrestrial intelligence, implied something important about either the prevalence of life or the durability of civilizations, or the nature of the universe itself. He did not live long enough to see SETI as a formal program, or the discovery of exoplanets, or the measurements that established the true scale of the cosmos. But the question he asked at that lunch in 1950 remains unanswered. It remains perhaps the deepest unanswered question in science, and the emptiness of the universe is at its heart. Let us now talk about what the emptiness means at the smallest scale, at the scale of the quantum vacuum, in a way that goes beyond the introduction we have already given it. Because the quantum vacuum is not just an interesting physical curiosity, it is the foundation of everything, and its properties, the specific way in which the void is not empty at the quantum scale, determine every physical process that occurs in the universe, including the existence of matter itself. Quantum field theory is the most successful scientific theory ever developed in terms of the precision of its predictions and the breadth of its applicability. It describes the fundamental particles of matter and the forces between them as excitations of quantum fields that permeate all of space. The electron is an excitation of the electron field. The photon is an excitation of the electromagnetic field. The quarks that make up protons and neutrons are excitations of quark fields. Every particle in the standard model of particle physics, and the standard model accounts for essentially all of the observable behavior of matter and energy except gravity, is a ripple in a corresponding quantum field. These fields are present everywhere, in the densest matter and in the most perfect vacuum, in the interior of a neutron star, and in the space between galaxies. They are the fabric of the physical universe, not in a metaphorical sense, but in a literal one. Space is not empty and then filled with fields. The fields are what space is. The properties of the quantum vacuum, the ground state of all these fields simultaneously, are the properties of empty space itself. And the quantum vacuum is unstable in a very specific sense. It fluctuates. Virtual particle-antiparticle pairs are constantly appearing from the vacuum energy and annihilating each other in times so brief, on the order of 10 to the negative 21 seconds for electron-positron pairs, that they cannot be directly observed. They are called virtual particles not because they are not real, but because they exist for too short a time to be detected individually. Their collective effect on the physical vacuum is real and measurable. The Casimir effect we mentioned earlier is the most direct demonstration of this. Two uncharged metal plates placed very close together in a vacuum attract each other. The attraction arises because the metal plates alter the spectrum of virtual particle fluctuations between them. Certain wavelengths of vacuum fluctuations are excluded from the region between the plates because they don't fit. The vacuum between the plates has less energy than the vacuum outside them. This energy difference produces a force, an attractive force pressing the plates together, that has been measured with extraordinary precision and that agrees with the predictions of quantum field theory to a level of accuracy that makes it one of the most precise measurements ever made. The vacuum is not empty. It has structure, it has energy, it has fluctuations, and those fluctuations are not random noise. They are the ground state of the quantum fields that constitute physical reality, organized according to the mathematics of quantum field theory in a way that produces all the physical phenomena we observe. This leads to one of the deepest questions in physics. If the vacuum has energy, if empty space is not truly empty, but contains a real positive energy density from zero-point fluctuations, then that energy should gravitate. It should curve space-time. It should contribute to the expansion of the universe in exactly the way that dark energy does. And when physicists calculate how much vacuum energy quantum field theory predicts, they get the number that is 10 to the 120 times too large. This is not a small discrepancy. It is the largest discrepancy between theory and experiment in the history of physics. It means that either quantum field theory is wrong in some way that has not yet been identified, despite its extraordinary success in predicting every other quantity that has been measured, or some unknown mechanism is suppressing the vacuum energy to its observed small value. A mechanism that has not been discovered despite decades of effort, or both. The void is not empty, and the energy of the void is the most important and least understood physical quantity in the universe. Understanding the vacuum energy is not an academic exercise. It is central to understanding why the universe is the way it is. If the vacuum energy were as large as quantum field theory naively predicts it would be, the universe would have expanded so rapidly in its earliest moments that matter could never have clumped together to form galaxies and stars and planets. There would be no structure, no complexity, no chemistry, no biology, nothing. A vacuum energy 10 to the 120 times larger than observed would produce a universe in which the only things that exist are isolated particles in an exponentially expanding void, forever separated from each other by an expansion too rapid for any force to overcome. The fact that the vacuum energy has its observed tiny value, not zero, not the enormous value naive calculation predicts, but a specific small positive value that allows structure to form while still driving the gentle, accelerating expansion we observe, is one of the most mysterious facts about the universe. It appears fine-tuned to a degree that strains any conventional explanation. Either some unknown physical principle sets the vacuum energy to this specific value, a principle we have not discovered, or we live in one of an enormous number of different regions of a multiverse, each with a different vacuum energy, and we find ourselves in one where the value is compatible with the existence of observers, because in all the other regions, no observers could exist. Neither explanation is satisfying in the way that good physical explanations usually are. Both leave enormous questions open. The void is not empty, and the energy of the void is the most profound puzzle in contemporary physics. Let us now talk about what the emptiness means for the future. Because the universe is not static. The emptiness is growing. The voids are expanding. The matter is being carried progressively farther from everything else by the accelerating expansion driven by dark energy. The future of the universe is a future of increasing emptiness, of matter becoming progressively more sparse in the volume of observable space available to any given observer, until the emptiness becomes so extreme that the concept of structure itself ceases to apply. We have discussed the long-term future of the universe in other contexts, the heat death, the gradual extinction of stars, the eventual evaporation of black holes, the approach to maximum entropy over timescales of 10 to the 100 years and beyond. But the emptiness adds a specific dimension to this future that goes beyond entropy and thermodynamics. It is the dimension of isolation, of the progressive separation of matter from matter across distances that grow larger with every passing second, and that cannot be crossed by any signal or any traveller, as the expansion carries everything away from everything else faster than light. In the near-term future, in the next few billion years, the emptiness will grow, but the effects on the observable universe will be modest. The local group of galaxies, bound together by gravity, will remain together. The Milky Way and Andromeda will merge in approximately 4.5 billion years, producing a single large elliptical galaxy that astronomers sometimes call Milkomeda. The other galaxies of the local group will gradually be drawn together into this central merger. The result will be a single large structure containing all the gravitationally bound mass of the local group, held together by gravity against the expansion of the universe in the same way that the expansion cannot pull the Earth out of the solar system because the Sun's gravity binds it. But everything beyond the local group, Every galaxy in the Virgo supercluster, every structure in the cosmic web beyond our local gravitational island is already receding from us at speeds that will only increase as dark energy continues to accelerate the expansion. The most distant galaxies visible to us today are already receding at speeds exceeding the speed of light, which is possible because they are moving with the expansion of space rather than through space. Their light is reaching us now only because they were much closer when they emitted it. The light they are emitting today, the light that represents those galaxies as they currently exist, will never reach us. The space between us is growing too fast for it to cross. As time passes, the galaxies visible in our sky will become fewer. The light from the most distant ones will be redshifted into invisibility as the expansion carries them farther away and the photons traveling toward us lose energy to the stretching of the space they travel through. Eventually, in approximately 2 trillion years, a time so long that the current age of the universe is a small fraction of it, all galaxies beyond the local group will have receded beyond the point where their light can reach us. The observable sky will contain only Milkomeda and the handful of smaller galaxies gravitationally bound to it. The emptiness will be complete, in the sense that matters for observation. Not complete in the absolute sense, all those other galaxies will still exist, still full of stars and planets and whatever forms of complexity the universe has produced in them by then. But complete in the operational sense, invisible, unreachable, beyond any possible communication or contact, as effectively absent from the experience of any observer in the local group as if they had never existed. The future universe is a universe of isolated islands. Each gravitationally bound structure, each local group, each cluster that manages to hold itself together against the expansion is an island in an expanding void, separated from every other island by distances that grow larger with every passing second, and that will eventually exceed any conceivable possibility of contact. The cosmic web, rich and structured and complex as it appears today, will dissolve, not because the matter in it disappears, but because the expansion carries the filaments apart until they are no longer structures, until the nodes are no longer connected, until every island is alone in a void too large to cross. The stars within each island will burn for their allotted time, hundreds of billions of years for the most common, smallest red dwarf stars. Then they will die one by one, and the islands will go dark. The matter that composed them, the carbon and oxygen and iron produced by stellar nucleosynthesis over billions of years of stellar evolution, will remain. Cold and dark and dispersed, orbiting in the dim halo of what was once a galaxy, in a universe so dark and cold that the background radiation temperature has dropped to within a small fraction of a degree of absolute zero. And even then, the emptiness will not be complete, because the quantum vacuum will still be there, still fluctuating, still containing its zero-point energy, still producing virtual particle pairs that appear and annihilate in times too brief to observe. In the coldest, darkest, most apparently empty future of the universe, the void will still contain energy. The nothing will still be something. The quantum fields that constitute the fabric of physical reality will still be present in their ground state, still organizing the properties of space according to the mathematics of quantum field theory, still maintaining the physical laws that govern the creation of stars and planets and life and intelligence in the warm, brief chapter of cosmic history when matter concentrated and complexity flourished. The emptiness of the universe is not the end of the story. It is the context within which the story occurs. The rare concentrations of matter in the voids and filaments, the galaxies, the stars, the planets, the living things that have arisen on at least one of those planets, are not somehow less real or less significant because they are surrounded by vastness. They are more remarkable, more extraordinary, more worth paying attention to. Consider what it means to be matter in this universe. To be a concentration of atoms held together by chemical bonds, organized by biological processes into structures capable of metabolism and reproduction and sensation and thought, on the surface of a rocky planet orbiting a star in a galaxy that is itself a tiny concentration of matter in a vast, empty cosmos. You are one of the rarest things in the universe. Not just rare in the way that gold is rare or diamonds are rare. Rare in the way that organized complexity itself is rare. In the way that the conditions that produce it are vanishingly unusual against the backdrop of what space mostly is. Space is mostly void, the quantum vacuum, dark energy, the trace wisps of interstellar medium between the stars, the cosmic microwave background radiation, 2.7 Kelvin, filling all of space with the faint afterglow of the Big Bang. These are the dominant contents of the universe by volume. Everything else, everything that any human being has ever seen, touched, thought about, built, destroyed, loved, feared, or imagined, is a tiny exception to the overwhelming rule that the universe is empty. The chair you are sitting on, the floor beneath it, the building around you, the city, the continent, the planet, the solar system, the galaxy. All of it, assembled together and compressed to the density of atomic nuclei, would fit in a volume smaller than a grain of sand. All of it, in the context of the observable universe, is less than a rounding error. And yet, it is everything that any conscious being has ever experienced. It is the entirety of what we know. It is the world. The emptiness of the universe does not diminish the world. It reveals its nature. It shows what an extraordinary thing it is to be a concentration of matter complex enough to experience anything at all, in a cosmos that is, by overwhelming volume and by the dominant physics of the quantum vacuum and dark energy and the vast, cold voids between the structures of the cosmic web, essentially and profoundly and almost perfectly empty. You are a rare thing in a vast emptiness. You are made of atoms that are themselves mostly void. You are living on a planet that is a speck in a solar system, that is a speck in a galaxy, that is a speck in a cosmos that is 99.9999+% nothing. And you are here, aware of it, thinking about it, finding it remarkable. That is perhaps the most remarkable thing of all. Let us talk about what physics actually says is in the void, not the summary version, the detailed version. Because the void is not a simple thing, and its contents, the things that fill apparently empty space at the deepest level of physical description, are among the strangest and most consequential facts known to science. We have established that the quantum vacuum contains zero-point energy and fluctuations. But there is more to the void than vacuum energy. There is the question of what space itself is. Whether space is a container that fields and particles exist within, or whether space is itself constituted by something. Whether the geometry of space-time is a fundamental feature of reality, or an emergent property of something deeper that we have not yet identified. General relativity, Einstein's theory of gravity, describes space-time as a dynamic entity, a four-dimensional fabric that curves in response to the presence of mass and energy, and whose curvature is what we experience as gravity. In general relativity, space is not a passive container. It is an active participant in physics. It bends around massive objects. It expands as the universe evolves. It can carry gravitational waves, ripples in its own curvature that propagate at the speed of light and that were detected for the first time by LIGO in 2015, when two black holes collided 1.3 billion light-years away. Space itself vibrated. The void oscillated. The fabric of space-time rippled like the surface of a pond after a stone has been thrown into it. Except the pond was the structure of reality itself, and the stone was the collision of two objects, each dozens of times more massive than the Sun. This is deeply strange if you think about it carefully. Space is not nothing. It has properties. It can be curved. It can carry waves. It can expand. It responds to the presence of matter and energy according to precise mathematical laws. It is, in some meaningful physical sense, a thing, a real physical entity with real physical properties, rather than an absence of things, which is what the word empty usually implies. And quantum mechanics makes space-time even stranger. At the scale of the Planck length, approximately 10 to the power of -35 meters, the smallest length scale at which the concept of distance has any physical meaning in current theory, the smooth continuous space-time of general relativity breaks down. At this scale, quantum fluctuations in the geometry of space-time itself become significant. Space is not smooth at the Planck scale. It is foamy, turbulent. The metric, the mathematical structure that defines distances and angles in space-time, fluctuates wildly at scales below the Planck length, producing a foam-like structure where the topology of space itself changes from moment to moment, where tiny wormholes and tunnels and handles appear and disappear in the fabric of reality at rates determined by quantum uncertainty. This is called space-time foam, and it was proposed by John Archibald Wheeler in the 1950s as a consequence of taking both general relativity and quantum mechanics seriously at the same time. If gravity curves space-time, and if quantum mechanics requires that the energy of any physical system fluctuates at the quantum scale, then the geometry of space-time itself must fluctuate. The curvature of space, the thing that we experience as gravity, must be subject to quantum uncertainty. And at sufficiently small scales, that uncertainty dominates, producing a chaotic, foamy structure that bears no resemblance to the smooth space-time of ordinary experience. We cannot observe space-time foam directly. The Planck scale is 20 orders of magnitude smaller than the scale of atomic nuclei, as far below the nucleus as the nucleus is below a centimetre. No experiment currently conceivable can probe that scale directly. Space-time foam is a theoretical consequence of combining two extremely successful theories in a regime where neither has been tested. It may be correct. It may be modified or replaced by the theory of quantum gravity that we do not yet have. But it illustrates something important about the nature of the void. That even at the smallest possible scale, even in the most apparently empty region of space, the void is not static and featureless. It is dynamic. It fluctuates. It has structure. It is not nothing. The void contains another thing that we have not yet discussed in detail: neutrinos. Neutrinos are fundamental particles produced in enormous quantities by nuclear processes in stars, by radioactive decays, by cosmic ray interactions with the atmosphere, and by the Big Bang itself. They are extraordinarily light. The heaviest neutrino has a mass less than 1/1,000,000th of the electron's mass, and for decades they were thought to be completely massless. They interact with matter only through the weak nuclear force and gravity, the two weakest forces at the scales of ordinary matter. This means they pass through matter almost entirely unimpeded. The Sun produces approximately 10 to the power of 38 neutrinos per second. At any given moment, approximately 65 billion solar neutrinos are passing through every square centimetre of your skin that faces the Sun, through your body, through the Earth, through everything, without stopping, without interacting, without any detectable effect on you or on the matter they pass through. The universe is filled with neutrinos. The cosmic neutrino background, the neutrino equivalent of the cosmic microwave background, produced when neutrinos decoupled from the rest of matter approximately 1 second after the Big Bang, fills all of space with approximately 336 neutrinos per cubic centimetre. 336 neutrinos in every cubic centimetre of space. In the air around you, in the space inside your body, in the apparent void of interstellar space. They pass through everything without interacting, carrying information about the earliest moments of the universe's history, about processes that occurred before the cosmic microwave background was emitted, before any atom had formed, in the first seconds of cosmic time. We cannot directly observe the cosmic neutrino background. Detecting neutrinos at all requires enormous detectors, tanks of hundreds of thousands of tons of ice or water or liquid scintillator buried deep underground to shield them from the constant rain of cosmic rays that would otherwise overwhelm the signal. Even then, detecting individual neutrinos requires waiting for the rare occasions, perhaps a few per day in a detector the size of a large building, when a neutrino happens to interact with a nucleus in the detector and produce a flash of light or a charged particle that the detection system can record. The cosmic neutrino background, neutrinos are lower energy than the solar neutrinos that these detectors are designed to catch, making them even harder to detect. They have never been directly observed. Their existence is inferred from the physics of the early universe, and confirmed by the agreement between theoretical predictions and measurements of the light element abundances produced in Big Bang nucleosynthesis. They are there, 336 per cubic centimetre throughout all of space, and we have never directly seen one of them. The void is full of neutrinos passing through everything, full of gravitational waves rippling through the fabric of space-time from distant cataclysms, full of cosmic microwave background photons carrying the afterglow of the Big Bang, full of dark matter particles of unknown type distributed in halos around galaxies and in the filaments of the cosmic web, full of dark energy maintaining its constant energy density throughout all of space, full of quantum vacuum fluctuations in all the fields of the Standard Model, full of space-time foam at the Planck scale, if our theoretical expectations are correct. The void is extraordinarily full of things we cannot see or touch or interact with using ordinary matter. The apparent emptiness of space is a feature of how we interact with the universe, through electromagnetic forces, through the exchange of photons, through the push and pull of electron clouds, and not a feature of what space actually contains at the deepest level of physical description. This has implications for how we think about where we are. When you look at a clear night sky and see the darkness between the stars, you are not seeing emptiness. You are seeing a medium extraordinarily rich in things that do not interact with your eyes. The darkness is full, the void is occupied. The apparent nothing between the stars contains neutrinos and gravitational waves and dark matter and dark energy and quantum vacuum fluctuations and cosmic microwave background photons and the full apparatus of quantum fields in their ground state. None of it visible, all of it real. Now let us talk about why the specific emptiness of our universe, the specific ratio of matter to void, the specific distribution of that matter in filaments and voids, the specific value of the dark energy driving the expansion, appears to be extraordinarily well calibrated for the existence of complexity and life. Because this calibration is one of the most debated and most profound questions in contemporary physics and cosmology, and the emptiness of the universe is central to it. The universe we inhabit has several physical parameters that could, in principle, take a wide range of values, but that have specific values that appear to be necessary for the existence of any form of complex structure. Change them even slightly, and the universe becomes one in which atoms cannot form, or stars cannot ignite, or galaxies cannot assemble, or the elements heavier than hydrogen cannot be produced, or the universe collapses back on itself too quickly for anything to form, or expands so rapidly that matter is too dilute to ever concentrate into anything. The emptiness is directly implicated in several of these parameters. The density of the universe, the ratio of matter to space, is one of them. If the universe were even slightly denser than it is, gravity would have overcome the expansion early in cosmic history, and the universe would have collapsed back into a big crunch long before stars and galaxies could form. If it were even slightly less dense, the matter would have been too dilute for gravity to pull it into concentrations. It would have dispersed too rapidly. The cosmic web would never have assembled. Stars would never have formed. The actual density of the universe is extraordinarily close to the critical density that separates these two outcomes. So close that explaining this near-perfect balance is one of the primary motivations for the theory of cosmic inflation, which naturally drives the density to the critical value regardless of initial conditions. The dark energy density is similarly fine-tuned. As we have discussed, if the dark energy density were as large as quantum field theory naively predicts, 10 to the 120 times its observed value, the universe would have expanded too rapidly for any structure to form. The expansion would have overwhelmed gravity at all scales before any concentration of matter could develop. There would be no galaxies, no stars, no planets, no chemistry, no biology, no minds. The specific tiny value that dark energy actually has, large enough to produce the gentle accelerating expansion we observe, small enough to allow structure to form, appears to be precisely calibrated for the existence of a universe capable of producing observers. The strength of gravity relative to the other forces is another such parameter. Gravity is by far the weakest of the four fundamental forces, approximately 10 to the 36 times weaker than electromagnetism. This enormous weakness is what allows stars to burn for billions of years rather than consuming their fuel in a catastrophic explosion. If gravity were stronger, stars would burn hotter and faster, consuming their hydrogen in millions of years rather than billions, giving insufficient time for the complex chemical evolution of planetary surfaces that appears necessary for life. If gravity were weaker, gas clouds might not be able to collapse into stars at all. The thermal pressure of the gas might overcome the gravitational attraction and prevent star formation entirely. The ratio of the electromagnetic force to the strong nuclear force determines the stability of atomic nuclei and the possibility of chemistry. The specific value of the fine structure constant, the number that characterizes the strength of the electromagnetic interaction, determines whether atoms can form and whether the chemical bonds between them have the right properties to support the complex molecular architecture of biological systems. Change it by a few percent in either direction, and the chemistry of life as we understand it becomes impossible. The list goes on. The mass ratio of the proton to the electron, the number of spatial dimensions, the specific values of the quark masses, the strength of the weak nuclear force that governs radioactive decay and the nuclear reactions in the Sun. At every level of physical law, at every scale of physical description, the universe appears to be calibrated, its parameters set to specific values in a specific combination, in a way that allows matter to concentrate and stars to form, and elements to be produced, and planets to exist, and chemistry to operate, and biology to develop, and minds to arise. This calibration could mean several things. It could be pure coincidence. The universe simply has the parameters it has, and we happen to be the kind of observers that can only exist in a universe with these parameters. The apparent fine-tuning is an artifact of the anthropic selection of observers. We cannot observe universes incompatible with our existence, and so all we ever see is a universe compatible with our existence, which gives a misleading impression of precision, because it excludes from our view the vast majority of possible universes in which no observation occurs. It could mean that there is a deeper physical law, undiscovered, perhaps undiscoverable given the current state of physics, that fixes the values of these parameters on the basis of some mathematical consistency condition or symmetry principle that we have not yet identified. That the apparent fine-tuning is not fine-tuning at all, but necessity. That these are the only values consistent with a mathematically coherent physical theory, and that understanding the theory fully would reveal why the constants must have these values rather than any others. Or it could mean that the universe we inhabit is one of a vast ensemble of universes, the multiverse produced by eternal inflation, each bubble universe with its own values of the physical constants. And the specific values we observe are not the result of any law or any coincidence, but of the selection effect of occupying one of the rare bubbles where the constants are compatible with complex structure and conscious observers. None of these possibilities has been established. The question of why the universe has the parameters it has is one of the deepest open questions in physics and cosmology. But the emptiness of the universe, the specific ratio of matter to void, the specific value of the dark energy that fills the void, the specific balance between the gravitational tendency to concentrate and the expansive tendency to dilute, is central to it. The universe is as empty as it is for reasons that are either coincidental or necessary, or the result of selection from a larger ensemble. And the question of which is the case is the question of why anything exists at all, in the form it does, rather than in some other form, or not at all. Let us talk now about what happens when you try to measure the emptiness. When you try to quantify how much of the universe is actually nothing, or at least as close to nothing as any physical system can get, the emptiest regions of space are the cosmic voids, the vast underdense regions that occupy most of the universe's volume between the filaments of the cosmic web. The Bootes void is perhaps the most famous, 330 million light-years in diameter, containing only a handful of galaxies, where a typical region of that size might contain thousands. But even the Bootes void is not truly empty. It contains the cosmic microwave background radiation. It contains dark energy at its usual density. It contains dark matter, though at lower density than the surrounding filaments. It contains neutrinos passing through it. It contains the quantum vacuum with its zero-point energy. It is simply a region where ordinary matter, baryonic matter, atoms and ions and electrons, is extremely sparse. How sparse? The average density of the universe, counting all matter, dark and baryonic, is approximately 9.9 times 10 to the negative 27 kilograms per cubic meter. That is approximately 6 proton masses per cubic meter. 6 protons in a volume the size of a large refrigerator. In the cosmic voids, the density is perhaps 10 to 20% of this already extraordinarily small value. In the filaments and galaxy clusters, it is orders of magnitude higher. But the average across all of space is 6 protons per cubic meter. For comparison, the density of water is approximately 10 to the 30 proton masses per cubic meter. The density of air at sea level is approximately 1.2 kilograms per cubic meter, or roughly 7 times 10 to the 26 proton masses per cubic meter. The density of the universe as a whole is approximately 10 to the 56 times less dense than air, 1 followed by 56 zeros times less dense. These numbers do not convey their own magnitude in any useful way. They are simply too extreme for human intuition to work with. What they represent is a universe in which the matter that we are made of, and that makes up everything we have ever directly interacted with, is distributed so thinly that its average presence in any given cubic meter of space is 6 individual protons. Everything else, the chair, the floor, the building, the planet, the solar system, the galaxy, is a local concentration of matter so extreme by cosmic standards that it constitutes an almost miraculous exception to the dominant emptiness. The best vacuum that human technology has ever produced in a laboratory, evacuating a chamber to remove as much matter as possible, achieves pressures of approximately 10 to the negative 12 pascals, corresponding to a density of roughly a few thousand particles per cubic centimeter. This is the best we can do, and it is orders of magnitude denser than the average density of the universe. The cosmic average is a better vacuum than the best vacuum we can make. The universe itself is emptier than any chamber we have ever evacuated. And the best vacuum we can make is not truly empty either. Even in the most perfectly evacuated chamber, the quantum vacuum remains. The virtual particle fluctuations continue. The zero-point energy of the quantum fields is present and measurable. The cosmic microwave background photons are present at their 2.7 Kelvin equilibrium temperature. The neutrinos are present, passing through the chamber walls as if they were not there. The dark energy is present. The dark matter is present. We cannot make empty space. We can only make space that is empty of ordinary matter. The deeper contents of the void, the quantum fields, the dark energy, the neutrino background, the gravitational wave background from the early universe, and from every black hole merger and neutron-star collision that has occurred since, cannot be evacuated. They are present everywhere, because they are properties of space itself, and of the fundamental fields that constitute physical reality. To remove them, you would not be creating a better vacuum. You would be destroying space. This is what the emptiness of the universe actually is. Not an absence of things, a presence of things so different from ordinary matter, so weakly interacting, so uniformly distributed, so deeply embedded in the fabric of space, that they are invisible to ordinary observation and impossible to remove by any process of evacuation or isolation. The universe is full of things that do not interact with us. It is empty only from the perspective of beings made of ordinary matter, using ordinary senses to interact with their environment. From the perspective of a neutrino, if neutrinos could have perspectives, the universe would look very different. Dense everywhere, full of material. Every cubic centimeter of space rich with the 336 neutrinos per cubic centimeter of the cosmic background, plus the solar neutrinos streaming out from every star, plus the supernova neutrinos from the occasional stellar catastrophe, plus the atmospheric neutrinos produced by cosmic rays. A universe far less empty than it appears to us, because the things we cannot see are visible to it. From the perspective of a dark matter particle, again, if dark matter could have perspectives, the universe would be different again. The dark matter halos of galaxies, invisible to us except through their gravitational effects, would be the dominant structures. The ordinary matter in the galactic disk would be a thin, bright layer embedded in a vast dark halo that extends far beyond the visible galaxy in every direction. The filaments of the cosmic web would be dark matter structures first, ordinary matter second. The dark scaffolding that organized the distribution of baryonic matter before stars and galaxies formed. We experience the universe from the perspective of ordinary baryonic matter: atoms, molecules, cells, organs, brains, tools, telescopes. And from that perspective, the universe is mostly empty, because ordinary baryonic matter is the rarest of its major constituents, constituting only 5% of the total energy content and less than 1% of the total volume in any form that we can directly detect and interact with. But the universe from other perspectives is not empty. It is rich and complex and full of structure and activity at every scale. We just happen to be the kind of thing that cannot see most of it. We happen to interact with the universe through the electromagnetic force and through gravity, and the things that dominate the universe's volume, dark matter and dark energy, interact with us only through gravity. The darkness is not absence, it is presence of a different kind. The void is not nothing, it is something we do not yet know how to see. This is perhaps the deepest implication of the universe's emptiness. Not that most of the cosmos is barren and dead and devoid of significance, but that most of the cosmos is full of things that we cannot yet perceive or understand. Things whose nature and properties are among the most important unsolved problems in physics. Things that constitute 95% of the universe's total energy content, and that determine the large-scale structure and ultimate fate of everything that exists. We are standing in the middle of a cosmos that is overwhelmingly composed of things we cannot see. We can detect their presence through their gravitational effects on the ordinary matter we can see. We can measure their influence on the expansion of the universe and on the distribution of galaxies and on the bending of light around massive structures. We can describe their properties with mathematical precision sufficient to make predictions that agree with observations to several decimal places. But we cannot identify what dark matter is made of. We cannot explain why dark energy has the value it has. we cannot reconcile the quantum field theory prediction of vacuum energy with the observed value of the cosmological constant. We are standing in the middle of a mystery that fills every cubic centimetre of space that we have ever occupied or will ever occupy. A mystery that is not hidden at the edge of the universe or at the smallest scales of physical reality, but that is present everywhere, all the time, in the apparent void that surrounds every atom of matter and every breath of air and every moment of every day. The universe is 99.9999% empty, and the emptiness is the most important thing in it, the most consequential, the most mysterious, the most worthy of our attention and our wonder, and our most sustained and rigorous intellectual effort. We are small concentrations of rare matter in a vast void we do not understand. We are looking at the darkness and trying to understand what it is. We are making progress, slowly, incompletely, with great effort and frequent revision, and the occasional fundamental surprise that forces us to rebuild our understanding from a different foundation. But we are looking, we are asking. We are reaching into the darkness with our instruments and our mathematics and our ingenuity, and finding that it is not empty, that it is not nothing, that the void is full of things that matter enormously for the structure and fate and meaning of the universe, and that we have not yet finished understanding any of them. The emptiness is not the absence of something worth knowing about. It is the presence of everything we have not yet learned to see. Let us talk about consciousness in the void. Because the emptiness of the universe raises a question that physics alone cannot answer, but that physics makes unavoidable, the question of what it means that a universe almost entirely composed of void has produced in at least one location matter organized into structures capable of being aware of the void that surrounds them. Consciousness is the most intimate fact of existence. It is the thing you are most certain of, more certain than you are of the external world, more certain than you are of the reliability of your senses, or the accuracy of your memories, or the validity of your reasoning. Whatever doubts you might entertain about the nature of reality, or the reliability of perception, the fact that you are experiencing something right now, that there is something it is like to be you, reading these words in this moment, is beyond doubt in a way that nothing else is. Descartes built his entire philosophical system on this single certainty. I think, therefore I am. Whatever else might be an illusion, the experience of thinking is real, because the illusion is itself an experience, and experiences require an experiencer. And yet physics, the most successful enterprise in the history of human knowledge for understanding the structure of reality, has almost nothing to say about consciousness. Quantum mechanics describes the behavior of electrons and photons and quarks with extraordinary precision. General relativity describes the curvature of space-time by mass and energy with extraordinary precision. The standard model of particle physics accounts for essentially all of the observed behavior of matter and energy, except gravity. Thermodynamics explains the direction of time and the approach to equilibrium. Evolutionary biology explains the diversity and complexity of living things. Neuroscience maps the structure and function of the brain with ever-increasing resolution. None of these disciplines, individually or collectively, explains why there is something it is like to be a brain processing information rather than nothing. This is the hard problem of consciousness, articulated most clearly by the philosopher David Chalmers in the 1990s. The easy problems of consciousness, explaining how the brain integrates information, how it directs attention, how it distinguishes sleeping from waking, how it produces reports about its own states, are scientifically tractable. They are difficult problems in the ordinary sense of requiring considerable effort and ingenuity to solve, but they are, in principle, solvable by the methods of neuroscience and cognitive science and information theory. They reduce to questions about the functional organization of neural systems. The hard problem is different. It is the question of why any physical system, however complexly organized, should be accompanied by subjective experience at all. Why there should be an inside to the process, a felt quality, a what it is like, rather than information processing occurring in the dark. No one has solved the hard problem. No scientific theory currently accounts for the existence of subjective experience. The neural correlates of consciousness, the brain states that accompany particular conscious experiences, have been studied extensively and with increasing precision, and this research is valuable and important. But identifying which brain states accompany which experiences does not explain why those brain states are accompanied by experience at all, rather than occurring as dark computation with no inner life. The correlation does not explain the generation. The map does not explain the territory. Some philosophers and scientists argue that consciousness is an emergent property of sufficiently complex information processing. That when a physical system reaches a certain threshold of complexity and integration, experience inevitably arises from it, in the same way that temperature emerges from the collective motion of molecules, or wetness emerges from the collective behavior of water molecules. This view, sometimes called functionalism or computationalism, has the virtue of making consciousness in principle explicable in physical terms. But it does not actually explain why complex information processing should be accompanied by experience. It identifies a correlation and proposes that the correlation is fundamental, without explaining why. Others argue that consciousness is a fundamental feature of reality, not something that emerges from matter under certain conditions, but something that is present at all levels of physical organization, perhaps even at the level of elementary particles, and that becomes richer and more complex as physical systems become more integrated and more complex. This view, called panpsychism in its various forms, has ancient roots, and has gained renewed philosophical attention in recent decades as a potential solution to the hard problem. If experience is fundamental rather than emergent, then the hard problem dissolves. There is nothing to explain about why physical processes are accompanied by experience, because experience is what physical processes are at every level. But panpsychism raises its own difficulties, including the combination problem. How the micro-experiences of elementary particles combine to produce the unified, rich experience of a conscious human being, that have not been satisfactorily resolved. Others argue that consciousness is simply beyond the reach of scientific explanation, that the subjective, first-person nature of experience is categorically different from the objective, third-person descriptions that science produces, and that no amount of neuroscientific or physical knowledge about brains and matter will ever bridge the gap between the description of a neural process and the experience of seeing red, or feeling pain, or understanding a mathematical proof. This view, the new Mysterianism associated with the philosopher Colin McGinn, holds that human cognitive faculties evolved to solve practical problems in a medium-scale physical environment are constitutionally incapable of solving the hard problem. Not because the problem has no solution, but because we lack the mental equipment to find it. Whatever the ultimate answer, And it may be that the ultimate answer is not findable by minds of the kind we have. The existence of consciousness in this universe is the most extraordinary fact about it. More extraordinary than the cosmic web, more extraordinary than black holes or neutron stars or the quantum vacuum, more extraordinary than the fine-tuning of the physical constants. Because all of those things, however remarkable, are just things, structures in the void, processes occurring according to physical laws. The cosmic web is extraordinarily large, but it does not know it is large. Black holes are extraordinarily dense, but they do not experience their own density. The quantum vacuum is extraordinarily energetic, but it does not feel the energy. The constants of nature are extraordinarily well calibrated for the production of complexity, but the calibration does not have the experience of being calibrated. Only in the rare concentrations of ordinary matter, organized into the specific kind of complex information processing systems that brains are, in at least one location in the observable universe, on at least one planet, for at least several 100 million years, has the universe produced something that experiences itself, something that knows it exists, something that can look at the void surrounding it and recognize the void as a thing worth looking at, something that can feel the weight of the emptiness and find it remarkable. You are that something. The universe has, in you, produced a local structure capable of contemplating the universe. The void has produced an island of experience. The emptiness has created something that finds the emptiness extraordinary. This is either the most expected thing in a universe full of life and consciousness that we have not yet discovered, or the most improbable thing in a universe that is otherwise entirely indifferent to the existence of experience. We do not know which. We cannot yet know which, but we know that it happened at least once, and that the happening of it, the emergence of a cosmos-contemplating mind from the void, is the most significant fact about the universe that we are aware of. Let us now talk about what the emptiness of space actually looks like when you try to depict it accurately. Because our representations of the cosmos, the images and diagrams and animations that communicate scientific ideas about space, almost invariably misrepresent the emptiness in a fundamental way. The images from the Hubble Space Telescope, the James Webb Space Telescope, ground-based observatories, these images are among the most beautiful and widely shared scientific products of our era. They show nebulae in vivid colours, galaxies in intricate spirals, clusters of stars in dense arrangements, the large-scale structure of the cosmic web mapped by surveys of millions of galaxies. They are extraordinary images. They are also profoundly misleading about the actual nature of space. The colours in most space images are false. The Hubble Space Telescope captures light across a range of wavelengths, assigns different colours to different wavelengths for visual clarity, and produces images of stunning visual richness that bear no resemblance to what you would see with the naked eye if you were present at the location being imaged. The Pillars of Creation, one of the most iconic Hubble images, showing towering columns of gas and dust in the Eagle Nebula, appear in vivid greens and reds and blues in the famous image. In visible light, they would appear as dim brown-grey wisps against a dark background, largely invisible to the naked eye. The colour mapping serves scientific purposes. Different wavelengths carry different physical information, but it creates a visual impression of richness and density and colour that the actual scene does not possess. The scale is also systematically misrepresented. In order to show multiple objects in the same image, astronomical images necessarily compress enormous distances into small frames. The famous image of the Andromeda galaxy shows the entire galaxy, 220,000 light-years in diameter, in a single frame. The image gives the impression that Andromeda is close enough to be seen in its entirety as a coherent object. In reality, Andromeda is 2.5 million light-years away, and its light has been travelling for 2.5 million years to reach the telescope that captured the image. What the image shows is not what Andromeda looks like from close range. It is the collective light of 1 trillion stars arriving at a detector after a 2.5 million year journey across expanding space. The diagrams of the solar system are even more egregiously misleading about scale. In any diagram where the Sun and all the planets are visible simultaneously, where you can see Neptune and the Sun in the same image, the distances between the planets and the sizes of the planets relative to the distances between them are necessarily distorted by factors of tens of thousands. An accurately scaled diagram of the solar system, where the Sun is the size of a grapefruit, would need to be approximately 2 kilometers in diameter to fit all the planets, and the planets themselves would be smaller than specks of dust. The most accurate representation of space would be almost entirely black, a vast darkness with occasional tiny points of light, separated by distances so enormous that their scale cannot be conveyed in any image that a human eye could usefully process. The overwhelming visual impression of an accurate representation of the universe would be nothing. The structure, the galaxies, the filaments, the clusters, the nebulae, the stars, would require extraordinary magnification and false color processing to be visible at all against the dominant background of empty, dark space. This is not a criticism of the images that astronomers and science communicators produce. Those images serve important purposes. They communicate the beauty and complexity of the cosmos. They convey specific physical information about the objects depicted. They inspire public interest in science and exploration. But they create in the mind of anyone who sees them an impression of the universe as a rich, colourful, densely populated place, an impression that is the exact opposite of what the universe actually is at any scale relevant to navigation or existence. The universe is dark, it is cold, it is almost entirely empty. The richness in the images is the richness of extraordinary distances compressed into visible frames, of millions of years of light accumulation gathered in single exposures, of false colour mappings of invisible wavelengths into the visible spectrum. The universe itself, experienced from within it without technological amplification, would be experienced as darkness so profound that the word dark does not adequately describe it. The only light would be from the stars in whatever galaxy you happen to be in, points of light separated by years of travel time, surrounded by blackness that extends in all directions to distances no human mind can directly apprehend. This is where we live, in this darkness, on a small, warm planet orbiting one of those points of light shielded from the full experience of the cosmic void by our planet's atmosphere and magnetic field, and the light of our nearby star. Seeing the darkness only as a night sky, rather than as the all-encompassing condition of the universe that it actually is. The night sky is a window onto the darkness, not the darkness itself. The darkness itself is on the other side of that window, extending in every direction for 46 billion light-years, and beyond, into regions we cannot see, filled with the things that fill the void: quantum vacuum energy, and dark matter, and dark energy, and cosmic background radiation, and neutrinos, and punctuated, at vast intervals, by the local exceptions that are stars and galaxies, burning briefly against the overwhelming background of their own emptiness. We look at the night sky and we see the exceptions, the stars, the faint smear of the Milky Way, the occasional naked-eye galaxy in the right conditions. We do not see the rule, we do not see the void. We see the lights in the darkness, and we do not see how much darkness there is around and between them. The darkness does not show itself in any single glance, because the eye is drawn to the light, and the mind interprets the absence of light as simply the background against which the light appears, rather than as the dominant condition that the light is the exception to. But knowing what the darkness is, knowing what fills it, what constitutes it, what its properties are at the physical level, what it means for the structure and fate of the universe, and for the question of why anything exists within it, changes how the night sky looks. Not visually. The photons arriving at your retina are the same whether you know the physics or not. But experientially, the darkness between the stars is not absence, it is presence. It is dark energy maintaining its constant density throughout all of space. It is dark matter distributed in halos and filaments, too tenuous to see, but massive enough to govern the large-scale structure of everything. It is neutrinos passing through at 336 per cubic centimetre, through the atmosphere, through your body, through the earth beneath you. It is the quantum vacuum seething with virtual particle fluctuations. It is gravitational waves rippling through the fabric of space-time from collisions of black holes and neutron stars billions of light-years away. It is the cosmic microwave background photons, 2.7 Kelvin, the afterglow of the Big Bang, filling all of space with the most ancient light in the universe. The darkness is full of things you cannot see. The void is rich beyond the capacity of any human sense to directly perceive. And knowing this, sitting with it, letting it be as large and as strange and as consequential as it actually is, changes the experience of looking at the night sky from the experience of seeing points of light against a background of absence to the experience of seeing the visible exceptions to an overwhelming presence that is invisible but real, and that constitutes most of what the universe actually is. We are small things in a vast void. We are made of atoms that are themselves mostly void. We live on a planet that is a speck in a solar system, that is a speck in a galaxy, that is a speck in a cosmos whose dominant contents we cannot see or directly interact with. We have been here for a cosmic instant. We will be here for another cosmic instant, and then we will be gone, and the void will remain, full of its invisible contents, expanding into whatever the void expands into, for a time so long that the current age of the universe is, by comparison, too small to measure. And we know all of this. We have worked it out from first principles and from observation and from the accumulated effort of thousands of scientists across centuries of increasingly precise measurement. We have built instruments sensitive enough to detect a femtowatt of power from 14 billion miles away. We have built detectors sensitive enough to measure changes in length smaller than a proton from the gravitational waves of a black hole merger a billion light-years distant. We have built telescopes sensitive enough to image the first light of the universe from 380,000 years after the Big Bang. We have built particle accelerators that probe the structure of matter at energies 10,000 times higher than the rest mass of a proton. We have constructed theoretical frameworks that predict the behavior of matter and energy with precision to 12 decimal places. And we have found that the universe is 99.9999% empty. That the matter we are made of constitutes 5% of the total energy content of a cosmos that is otherwise filled with things we cannot identify. That the void is not nothing, but is instead the most consequential and least understood aspect of physical reality. That the quantum vacuum seethes with energy we cannot explain. That dark matter shapes the universe without interacting with light. That dark energy drives the expansion of the universe without any physical mechanism we can describe. That space-time itself is a dynamic medium that curves and waves and possibly foams at the smallest scales into a structure we cannot observe. We know all of this, and we do not fully understand any of it. We are standing in the middle of an overwhelming mystery, looking at it with every instrument we can build and every mathematical framework we can construct, making progress that is real and that matters and that changes what we know, and recognizing that the progress we have made reveals more of the mystery rather than less of it with every advance. This is where we are, in the void, made of the rare ordinary matter that constitutes 5% of the cosmic total, surrounded by darkness we cannot see through, equipped with minds that evolved to navigate a world of medium-sized objects at medium speeds, and that we have extended with enormous effort and ingenuity to grasp realities at scales from the Planck length to the observable horizon of the universe. Knowing more about the structure of reality than any previous generation of minds on this planet, understanding less than we eventually will, uncertain about things we will eventually be certain about, standing at the edge of knowledge in every direction, looking out into the darkness that is not empty, reaching into the void that is full of things we have not yet learned to see. The universe is almost entirely empty. The emptiness is the most important thing in it. We are the rare exception to the overwhelming rule of void. Tiny concentrations of organized matter in an expanding cosmos that is mostly dark and mostly cold and mostly composed of things that do not interact with us. We exist at the edge of understanding, in the brief, warm moment when the universe is still lit by stars, still rich enough in ordinary matter to support the kind of complex chemistry that produces minds, still young enough that the expansion has not yet carried all structure beyond the visible horizon. We are here now, in the light, in the warmth, in the brief interval between the beginning and the darkness that follows, looking at the void and finding it remarkable, understanding it imperfectly and reaching to understand it better.
Making sense of the emptiness with the tools that the emptiness has accidentally produced, with minds that are themselves made of the atoms that are themselves mostly void, organized into structures capable of contemplating their own composition and their own situation, and the strangeness and the scale and the beauty of the cosmos that contains them.
The emptiness is not the absence of meaning. It is the context within which meaning exists. The void is not the negation of what we are. It is the medium through which what we are has been made possible. The vast stage on which the rare miracle of organized matter and conscious experience has been able to occur.
The darkness is not the opposite of the light. It is what makes the light visible. The emptiness is not the opposite of existence.
It is what existence emerges from, and what it is embedded in, and what it will return to when the brief, warm chapter of cosmic history in which stars burn and planets exist and minds arise has run its course. We are in the void. We are made of the void. We are looking at the void and asking what it is. And that, the looking, the asking, the sustained and curious and rigorous attention paid by organized matter to the emptiness that surrounds it, is perhaps the most extraordinary thing that has ever happened in the 13.8 billion year history of a universe that is 99.9999% empty. The moment is not comfortable. It is something closer to vertigo, the feeling of the ground dropping away, not physically but conceptually. The recognition that the solid, continuous, present world of ordinary experience, the chair, the floor, the body, the room, is at the level of atoms almost entirely nothing. That the solar system is almost entirely nothing. That the galaxy is almost entirely nothing. That the observable universe, containing 1 trillion galaxies, each containing hundreds of billions of stars, is in terms of the fraction of its volume occupied by anything we can touch or see or interact with, essentially nothing. That 95% of the total energy content of the cosmos is made of things we cannot identify. That the void is not the background against which existence occurs, but the dominant condition of which existence is the rare and temporary exception. The vertigo is real. It is appropriate. The universe is actually this way. The numbers are actually this large. The emptiness is actually this extreme. And sitting with that, letting it be as large as it is, without immediately reaching for something reassuring to push it back to a manageable scale, is one of the stranger and more important things a mind can do with itself. And then something else happens, after the vertigo. After the falling away of the familiar sense of a world that is solid and full and present in the way ordinary experience makes it feel, something quieter and more difficult to name. You are still here, after all of it. After the atom is revealed to be mostly void, and the solar system is revealed to be mostly void, and the galaxy is revealed to be mostly void, and the universe is revealed to be 99.9999% nothing, with the remaining fraction made mostly of things no one can explain. You are still here, present, aware, experiencing. The chair that is mostly empty space is still supporting your weight through the electromagnetic repulsion between electron clouds. The floor that is mostly empty space is still solid beneath it. The air that is mostly empty space is still filling your lungs. The body that is mostly empty space is still warm and breathing and feeling the slight weight of the darkness outside the window and the quiet of the room, and whatever small sounds are present in the space around you. The emptiness did not stop any of this from being real. It did not stop the world from being present, and the experience of it from being immediate, and the moment from mattering in the way that moments matter to things capable of experiencing them. The physics of the void does not subtract from the reality of the experience. It adds to it. It reveals what the experience actually is, an extraordinarily improbable configuration of mostly empty atoms, organized by evolutionary processes into a structure capable of receiving information about the cosmos and feeling something about what it receives. You are a rare thing. Not in the self-congratulatory sense of the word, in the physical sense. In the sense that the universe is almost entirely composed of things that do not experience anything. Dark energy uniformly filling the void, dark matter distributed in halos too tenuous to feel, quantum vacuum fluctuations arising and annihilating in intervals too brief to constitute experience, cosmic microwave background photons drifting through the darkness at 2.7 Kelvin, neutrinos passing through matter as if it were not there, none of it aware, none of it experiencing, none of it finding anything remarkable. And then there is you, an organized concentration of rare, ordinary matter, an exception to the dominant condition of the universe in multiple senses simultaneously. Matter rather than void, ordinary matter rather than dark matter, living matter rather than dead matter, conscious matter rather than merely metabolizing matter. An exception within an exception within an exception, within a cosmos that is almost entirely defined by what you are not. You are the universe's rarest configuration, the kind of thing that can look at the void and know it is the void. The kind of thing that can understand that atoms are mostly empty space and feel something about that understanding. The kind of thing that can grasp the scale of the cosmic web and the depth of the cosmic voids, and the improbability of its own existence in both, and find in all of it something worth attending to. The void produced you. Not intentionally, the void has no intentions. Not inevitably. The probability of any specific configuration of matter producing conscious experience is vanishingly small against the background of what matter mostly does, which is nothing. Not permanently. You are a temporary structure, organized for a time and then dispersed back into the atoms and molecules and energy that constitute the universe's more common conditions. But actually, really, the emptiness organized itself into something that experiences the emptiness and finds it remarkable. This is what happened. This is what is happening right now. The void is experiencing itself through you. The emptiness is aware of the emptiness because you are aware of it. The universe, which is 99.9999% nothing, whose dominant contents are unknown, whose fundamental nature at the deepest level is uncertain, which will expand and cool and darken for a time so long that the current age of the cosmos is by comparison essentially zero. The universe is, in this moment, in this room, through you, knowing that it exists. That is not nothing. In a cosmos that is almost entirely nothing, that is not nothing. That is the most extraordinary thing that happens anywhere in the observable universe, as far as we know. The most extreme exception to the dominant rule, the rarest configuration of the rare. Matter organized into awareness. The void knowing itself. The emptiness surrounds you in every direction. It extends 46 billion light years in every direction to the observable horizon and beyond into regions you will never see. It is filled with things you cannot detect and cannot explain and cannot reach. It will outlast you by a duration that makes every human concept of time irrelevant. It was here before you by 9 billion years and will be here after you by, effectively, forever. And you are in it, now, aware of it, finding it worth attending to. The universe is 99.9999% empty. And in the fraction of a percent that is not empty, in the rare concentration of ordinary matter on this small, warm planet, orbiting an unremarkable star, in the outer region of a spiral galaxy, in one small corner of the observable cosmos, something is here, present, aware, looking at the darkness and finding it full of meaning that the darkness itself did not put there. You put it there, by looking, by asking, by finding the emptiness remarkable. That is enough. In a universe almost entirely defined by void, the fact that anything finds anything remarkable is enough. It is, in fact, everything.